All right, in this video, we are going to be deriving the D6 character table from scratch. And so, uh, a lot of times with these tables and these point groups, a good first step is to visualize a molecule in that point group. You're going to have a hard time coming up with many molecules that fall into this category for D4. It's a chiral point group. But what I would do is, I'll show you this molecule here, the sulfur-containing molecule, just to help us visualize it. But what I would do is think about D4H symmetry, which is like a square, right? And just eliminate the mirror planes. And that's going to get you the same symmetry operations for this point group. And so that's what we're going to have to do first. We're going to have to generate all the symmetry operations for the point group. And so, of course, we're going to have identity. We are going to have a C4. It's a D4 point group after all. So that's going to be a 90-degree rotation. Now, along this 90-degree rotation, right, what other symmetry elements are we going to have? We are going to have a C4 twice. We can do C4 twice. Now, C4 twice is doing a 90 degrees twice. I use these hats, by the way, to note that we're talking about symmetry operations, not symmetry classes. So a C4 twice is going to be the same as a 180-degree rotation, which we just call C2. And then we also could do a C4 three times. Okay? That would be what, a 270-degree rotation. That's going to be unique. So those are unique operations. Now, if we do a C4 four times, that is just equal to back to identity. That's a 360-degree rotation. So that's not a unique operation. Okay, and then we know we're a D point group, so we're going to have perpendicular C2s. And we're always going to have N perpendicular C2s. This perpendicular sign. So this C2 is not perpendicular with the principal rotation axis, the highest order N. It is coincident with it, right? It's just a 180-degree rotation instead of a 90-degree rotation. What do I mean by N? I mean Dn. So we're D4 here. So we should have 4 perpendicular C2s. And those are going to be these 4 right here. And I've split these up into 2 groups just to help you visualize these a bit. You can see that, but let's write these down. So those are going to be C2 prime, we could call it. C2, I don't know, prime with a plus sign, just something to make it different. And then, I should be putting hats because these are operations. And then we're going to have C2, sorry, I should not call these primes. Let's call these just C2. Well, we do have to call them something. So let's call them, I don't know, C2 asterisk and C2 plus. I'm just giving them random symbols here to distinguish them from this C2. And then we're going to have C2, we can call it prime, and C2, maybe double prime. And visualizing these 4 different perpendicular C2s, you can see that they're actually doing different things. Okay, and so that's our next step, is to group these into classes. And so since we're talking about the perpendicular C2s, let's start there. And so you can see that these 2 perpendicular C2s are cutting through bonds. And these 2 perpendicular C2s are cutting through the sulfur atoms. And so they're going to be doing very different things in terms of the rotation. But these are similar. And these 2 that are cutting to the sulfur are going to be in their own class. So we'll call that C2 prime. And these 2 are going to be in their own class. So we'll call that C2 class. I drop the hats because we're talking about classes now. And we put 2 in front of it because there's 2 operations in each of these. Now, how do I know these are in different classes? mathematically is because there's no way to interconvert between these two groups of symmetry operations using other operations in the point group if we define different Cartesian coordinate systems. However, we can interconvert between these two. And so, really the way to think about this, it can get kind of tricky organizing these things into classes, but the way to think about it is, am I fundamentally doing different things to a molecule? And is there somewhere way to interconvert between these two different modes? And here we have, going through sulfurs, and here we have going through these bonds. So they're clearly different, but they're grouped. This C2, right, which is actually equal to the C42, is going to be even more different. So we're going to want to group identity in a class by its own. Identity is always in a class by itself. That one's easy. And the C4 and the C43 are going to go into their own class. We'll call that the 2C4 class. And why is that? Again, because if we do a clockwise rotation, or one-way rotation, we would be taking, doing 90 degrees, taking this sulfur atom into that sulfur atom. And if we did a C4 3 times, we would be taking that sulfur atom all the way to that sulfur atom. But if we just defined our axis systems in a different way, that would be equal to a C4, right? So the C4 and the C43 are sort of equivalent. It's arbitrary depending upon how you define your axis systems, and you can interconvert between those axis systems using some other operations, like namely these perpendicular C2s, to get you from one place to another. So those two are going to go together. This C2 is going to be by itself. And we're going to call that one C2 and just say equals C4 to C4 twice, just so we know, which one we're talking about. We could also call it C2Z, but that's how this is going to all pan out. So now that we have our 1, 2, 3, 4, 5 classes, we're going to be able to, we have 5 classes and we have 8 symmetry operations total, 1, 2, 3, 4, 5, 6, 7, 8. We're going to be able to write sort of the bones of our character table here, our skeleton. So how we do that, by convention, we put the point group of the character table in the top left, and then we draw out our classes that we had right there. So we had E, the identity. I don't use the hat notation because we're talking about classes here, not operations. And then we have our 2 C4s. Remember that included the C4 and the C43 operation. We have our C2, which is a C2Z, or we can write equals C42 to help us remember that it was a 180-degree rotation pointing upwards in the Z direction. And then we had the 4 perpendicular C2s grouped in 2 different classes. So we'll call them 2C2 and 2C2 prime. So those are our 5 classes. And if we have 5 classes, 1, 2, 3, 4, 5, one of our character table rules tells us we must have 5 irreducible representations, or I like to just call them vectors because that's what they are. We give them arbitrary names right now, gamma 1, gamma 2, gamma 3, gamma 4, gamma 5, because we don't know what the vectors are, so we can't assign the Mulliken symbols yet. But what we do know is that the first irreducible representation is always 1s across the board. So put that one in for all your character tables. Gamma 1 is always going to be 1s across the board. Totally symmetric representation. Now we start using our various character table rules. And one of our first rules is that the sum of the squares along the diagonal, the sum of the squares along the dimensionality refers to the character under the identity class, is going to be equal to the order of the point group. So what I mean by that, sum of the squares, I just call these, I want to figure out what A, B, C, D r as we derive this character table. So 1 squared plus a squared plus b squared plus c squared plus d squared is equal to the order of the point group, which is equal to the total number of symmetry operations in the point group, which we just found out was 8, but it's 1 plus 2 plus 1 plus 2 plus 2, right? Equals 8. And these values under the dimensionality, under the identity, have to be whole numbers. They have to be 1, 2, those are going to be the most common, and some higher symmetry point groups, 3, 4, and 5 are also possible, but normally 1 and 2. And so the only way to get this to work is if you have, with those constraints, is if you have all of them being 1s except the last one being 2, and 1 squared plus 1 squared plus 1 squared plus 1 squared equal plus 2 squared equals 8. So that's good. So now we can erase these A, B, C, Ds and just fill in 1, 1, 1, 2. All right, so now at this point, it's a good idea to start testing functions and seeing how these functions transform in the symmetry space to give us, you know, our different transformations, which then can help us figure out what some of these vectors are. So we're going to go through this, and what we're gonna do is look at so eventually what we're going to try to do is, you know, derive this whole entire character table with the different point groups. You can see they name the classes a little bit different. They call it C2Z. We talked about how we could have done that, and then that caused them to have them prime and double prime notation, but R prime won't be there, double prime, but it doesn't really matter what you call these things, right? As long as you know, what is what in each of these cases, you'll be fine. Okay, so let's go through and look at that, and we might need to refer back to these just to help us visualize some things. But let's go and look at the z vector. So we're going to test the z vector and see how it transforms. And I'm going to draw over here a coordinate system, x, y, z. Or z, remember, is always going to be a principal rotation axis. How you define the x and y doesn't really matter mathematically, although they all have to be perpendicular to one another, of course. So we're thinking about a z vector, so in red here. And so what happens when we do an identity operation to a z vector? We're going to march along and apply these different operations to the z vector. Well, identity doesn't change anything, so z goes to z. We have a 1-by-1 matrix that describes this, and we're going to take the trace of this matrix, or the character of the matrix, which is the sum across the diagonal. It's only a 1-by-1 matrix, so the character, or chi, the identity, is going to be equal to 1. Okay, now we do the C4. Now, do we do the C4-3 or the C4 once? Those are both in the same class. It doesn't matter. You're going to get the same answer. You're spinning across this way, but you have a vector that's pointing up, and if you rotate that that way, nothing changes, right? The head's still pointing up, straight up. So z is going to go to z, and the same logic, you're going to get a 1 here underneath for z. All right, for C4. Now, what about our C2? And if we want to match the nomenclature for the character table that we pulled up at the end there, we can do it this way. They call it C2Z, like prime and double prime. C2Z. Z is going to go to Z. We're just doing 180 degree rotation again on Z, and nothing happens. But what about C2 perpendicular? Well, that's a rotation along maybe the X, we could define it. So C2 prime right, is going to take z to negative z, because now you're flipping it, the z vector, this way. You're flipping this whole axis system that way. That z vector is going to go to the negative of itself as we flip along the x-axis. So I defined this one of the C2 primes that were, whichever one we chose here, as being x along the x. So that's going to be -1. And you can see that so this is a C2x, let's say, right? This would be our C2y. But now if we're thinking about our C2 double primes, they're going to be 45 degrees. So they're going to be, if this is our x-axis, then this is our y-axis. So then this C2 double prime is going to have to be bisecting the x and y axis. So we're talking about doing a rotation in this manner, right? That's our C2 double prime. This was our C2 prime that we chose, okay? But it doesn't really matter. It's a flip, right? It's still going to be z. This one's easy to visualize. I hope so. C2 double prime goes z to z because it's still a flip. It's still going to, doesn't matter what angle in this xy plane, or you're doing this 180-degree rotation, you're still going to take z going to z. So you're going to get -1 there. And that's how your function z is going to transform. So this is nice. It helped derive one of these parameters, one of these irreducible representations for us. Okay, so the next step is to choose some other function. And so we're going to choose x. Well, start out with x, y, and z. Those are good ones to choose with. Usually start with z, just because a lot of the point groups are defined with respect to their principal rotation axis. That's a high degree of symmetry there. So z usually transforms pretty simply. X is going to be a little more complicated. X is going to go to x. So now for clarity here, we are talking about doing the rotation of an x vector. Right? So identity is going to go to identity. What's going to happen with C4? Well, x is going to spin now. We're doing a C4z, 90 degrees. X is going to spin into y. And that's telling us that we have to define x in terms of y. So we also have to now start thinking about how y transforms. Identity, y is going to go to y. But for a C4 rotation, what is going to happen to a y? Well, if we started with a y here in, let's say, blue, and we spin that 90 degrees using this C4z, 90 degrees on C4, you can see it goes to -x. So y goes to -x. And so because y and x transform together, you kind of know you're dealing with gamma 5 here. You're dealing with the dimensionality being 2. There's 2 functions that transform together. Any function that transforms together has to have a pair. Where this comes from is now we're forced to keep these together. We use, for the identity operation, we use the identity matrix with 1s across the diagonal. And so our chi, our character of the E operation for xy function, x comma y function, is equal to the sum across the diagonals, or the trace, or the character of the matrix, equals 2, which is why we have a 2 there. Okay, and then we do a very analogous thing for the C4 operation. We write a matrix, and this is going to be zeros off the diagonal. And we're going to have 1s and -1s there. But really, and that's the matrix that takes x, y into y, comma minus x. You take the sum across the diagonal, 0 plus 0, and you get chi of C4 operation is equal to 0. And so we can then put in a big 0 there. What about our C2z? Well, if we do a 180-degree rotation across the z-axis, x is going to spin all the way around to minus x now. Back there. And y similarly would spin around to minus y. So we're going to get x goes to minus x, y goes to minus y. That's going to get us a matrix that looks like -1 on the diagonal. Take the trace of that matrix, -1 plus -1, and then get the character for the C2 operation, C2Z, is going to be equal to -2. So we can put a -2 here. And our next one is a C2 prime. It's going to give us some more space here. I'll call this a C2 prime. What's going to happen? Well, remember we defined our C2 prime as being along the x-axis. So if we're spinning along that same axis, x is just going to stay as x. We're spinning along that, so x stays at x. Y, however, is going to be flipped to -y. And so that gets us a matrix where we have 1 and -1 on the diagonal. And now we take the trace of this matrix and we get chi of C2 prime is equal to 1 plus -1, which is equal to 0. And so we put a 0 here. And our last one is a C2 double prime. And that is this one going kind of in between, right? Bisecting. So what's that going to do? That's actually going to, if we wrote it this way, right? And we have this arrow pointing here, that's going to flip this off axis here to actually go into -y. So maybe a little harder to visualize that one, but x is going to go into -y, and y is similarly going to go into x. It's kind of flipping over here, right, into this. So those are both going to result in off-diagonal components here. And so you're going to get 0, -1, 1, 0. That's going to be your matrix that describes this transformation. And you sum this across the diagonal, and your chi of C2 double prime is going to be equal to 0. So we got our 2, 0, -2, 0, 0. You can see that matches up actually with what the answer is. So we're looking good. Our last ones, we could test some other functions, and you could see, you know, we could test x squared minus y squared to xy. We can do that. That's one way of doing it, and I'll do it both ways. And so let's sure, we can do it both ways. So let's think about we're probably is best to keep these up here, because if we are going to use the more complicated functions, it's nice to have these written, and then we can erase this part to give us some more room. But another way, a faster way of doing this is just not to, you know, keep testing different functions, because you don't really know a priori what your answers are going to be. Are you going to generate a new vector, or are you going to generate one that you already generated? For example, if you tested RZ, you would just spit out back this second vector, which we already have, because we got that with Z. So at this point, what I like to do is just puzzle it out using the orthogonality principle. And so I know with the principle of orthogonality that the dot products of any two vectors have to equal 0. And so what that means is, for example, the easiest one mathematically to look at is dotting it with gamma 1. So I know I'm trying to figure out gamma 3 here. I know gamma 1 dot product with gamma 3 dot product of gamma 1 has to be equal to 0. And this dot product is a little special. It has to be normalized for the number of operations in each class. And so what I mean by that is one of the vectors you're going to have to multiply by the number of operations in each class. So gamma 1 is 1, comma 1, comma 1. Put myself down here. 1, comma 1, comma 1. Let's see, we need 5 ones dotted with 1, comma, we'll again call it A, B, C, D as we figure this out. A, B, C, and D equals 0, but now I have to adjust for the number of operations in each class. So we have to multiply one of the vectors by 1, 2, 1, 2, and 2. So one operation in the identity class, two operations in the C4V class, one operation in the C2Z class, two operations in the C2 prime class, and two operations in the C2 double prime class. So you end up with 1, 2, 1, 2, 2, dotted with 1, A, B, C, D, has to be equal to 0. And the thing about these character tables, when you have 1 under the dimensionality, you know that you're only gonna have ones or negative ones. That's just how it works. Mathematically, when the dimensionality is 1, when the dimensionality is 2 or some other, or 3 or 4 or 5, you can have any number actually be here, but for here you can't. So you're gonna have ones or negative ones. So then we just have to kind of think about this formula and think about how this is going to balance ourselves out, right? And so how are we going to be able to do that? And so if we test with, let's say, a -1 here, well, then what we can do is we can put a +1 there, and those two are going to balance each other out. What I mean by that is we have 1 times 1 times 1. This is all 1, so we don't have to worry about that. So really it's just 1 times 1 is a +1, and -1 times a -2. Now we're overall, -2 plus -1 was -1. And so here it's 1 plus 1. So remember that what the dot product is, just so clarity here, it's, you multiply all the components and then add them. So 1 plus 2a plus b plus c plus d has to equal plus 2c plus 2d has to be equal to 0. But so we got sort of these three components to balance each other out. Again, what I'm thinking about that is we have a +1 underneath a 1 here for identity. We have a +1 underneath a 1 here for C2Z, but we have a -1, we have two of those, we have a -1 worth 2, balancing it out, so it's equal to 0. So that tells me I'm going to have a +1 and a -1 here to keep the balance, because we got a 2 and a 2, keep the balance. And then it's pretty easy to see, oh, I could just do the same trick, but swap these, because I can make this a -1 and this a 1, and everything will be balanced. These three balance each other out, and these two balance each other out. So that's how I kind of think about this when I'm deriving it. So at this point, we actually derived the character table pretty much. The only other thing we have to do is add the Mulliken symbols, right? And so let's go through and do that. And then for fun, we'll show what the symmetries are for x squared minus y squared and x times y. Although, we didn't really have to do that to derive this character table, but it's just, nice to know where all these symmetries are coming from. So now we just have to assign Mulliken symbols. So we can get rid of our gamma 1, gamma 2, gamma 3, gamma 4, gamma 5. And our Mulliken symbol rules are that we give it an A or a B if we have a dimensionality of 1. Now, how do we choose between an A or a B? Well, if we're symmetric with the principal rotation axis, we give it an A. So the principal rotation axis is C4, and we got 1s there. We give it a B if we're antisymmetric, -1. So these are going to be B's, and we give it an E if we have a dimensionality of 2. Now, we can't have two things called A or two things called B, so we have to further distinguish these. And the way we do it is we just look at the next character that there's differentiation from. And so in this case, it's C2Zs are all symmetric, so that doesn't help us. So we're going to use this one. And so you can see what ends up happening is that you end up calling the subscripts 2's when you have a -1 under the primes, and 1's when you have a +1 under the primes. Now, it's sort of arbitrary whether or not you did that for the primes or double primes. You could imagine you switched your definitions of what the primes are and the double primes, this is where it can get complicated. And if you're not careful with what textbooks you're using, B1 and B2 could get switched on you because of this. So just be careful that you're using the same, you're talking the same language here. There's just a lot of things to keep track of these character tables, but in our case, we did end up doing it the way that that book or wherever got that text character table from. But anyway, I'm putting a 1 here because I have a positive 1 there. I'm putting a 2 there because I have a negative 1 there, 1 there because I have a positive 1 there, 2 there. That's the Mulliken symbols. Mulliken symbols aren't a perfect system because of some of this arbitrariness that can come up. Okay. The last thing I wanted to do was show you why the xy function transforms as B2, for example. So what we would do there in this case is pretty straightforward. We would just go through and go through the same sort of idea where you think about all the different transformations operations. So what does E do to xy? Well, it's identity, so xy goes to xy. What does C4 do, right? C4 do to xy. Well, what did C4 do to x? It took x into y. So if we have xy, x went to y, and y went into negative x. So that equals negative xy. So it went to its negative itself. What did C2z do to xy? Well, C2z took x to negative x and y to negative y. So that equals just xy. And what did C2 prime do? Well, C2 prime took x to x and y to negative y. So that's negative xy. So our characters, oh, not quite, one more left, C2 double prime, what did that do? That took x to negative y and y to x, y to negative x, sorry. And so, what did that end up doing? That took x, y to xy. So that ends up getting us a xy there. So then you just go through here and say, okay, xy went to xy, 1, negative 1, 1, negative 1, and 1. And so xy transforms as B2. And so you can see that right here, how we got that. So that's just one example. You can do it for some of the other formulas as well.